Do you know what parallel means? Parallel lines move in the same direction. And so here's an example of two parallel lines on the flat plane, which is the surface of my board. And parallel lines run in tandem, side by side. They never cross. They never intersect. Well, some mathematicians have defined it as they intersect at infinity. All right, that's a little bit of hair splitting for mathematical purposes. We can't get to infinity, so for all practical purposes, parallel lines do not intersect, do not cross. All right. It gets a little more interesting if you change your geometry, because this is good old-fashioned Euclidean geometry, over 2,000 years old, where we dealt with a world which had flat surfaces, or in 3 dimensions has length, width, and height. It was around the first half of the 19th century, people began to wonder, well, what happens if you change the geometry to, say, a sphere? For example, on the surface of the Earth, longitude lines are considered to run parallel to each other, and yet, and I haven't drawn this very well, longitude lines, although they run parallel on the surface of the Earth, they do intersect at the North Pole and South Pole. So if you're driving due north on one road and someone else is driving due north on another road, if those roads were to continue going north, you're driving parallel, but yet you're going to meet at the North Pole if you can get there, or at the South Pole. So the notion of parallel begins to get altered when you change the geometry that you're thinking about. That was a very profound realization in the early 19th century, and people started working in other kinds of geometries, and it turns out the physicists picked this up. And in fact, it was Albert Einstein who realized that the geometry of space can be somewhat curved. For example, a large body, such as the sun, literally bends the space around it. And the sun is so enormously massive that a ray of light passing near the sun actually gets slightly bent toward the sun. And so it doesn't travel strictly in a straight line. Well, this was confirmed, incidentally, in a famous experiment in 1919 during a solar eclipse, where the planet Mercury was observed to be in a slightly different position than where we knew it really was. And that's because, since it was right positioned near the edge of the sun, from our point of view, its rays of light were bent around the sun, and so it created an illusion which Einstein had predicted in 1915. So physicists like to worry about those things, and of course so do some mathematicians. This is called non-Euclidean geometry. All right, well, I'll get back to the down-to-earth stuff here. Find the equation of the line passing through the point 3, 4 and parallel to the line y equals to negative 2/3 x plus 7. So, for our purposes, what are we concerned about? The slopes of parallel lines have to be equal, because if the slope describes direction, then these two parallel lines have the same slope values. So I've written an equation where it's easy to find the slope. This line is, and I'm just sketching it roughly here, 7, negative 2/3. So it comes down approximately like this. There's my negative 2/3 slope. But we're interested in a different equation, one which passes through the point 3 comma 4, which is, we'll say down here, 3 comma 4. And so we're looking for this line, which runs parallel. What is the equation of that line? So I like these problems because you're given information and you're supposed to assimilate that information and figure out what to do with it. And so given this line, what is that line? Well, because it's parallel, it has the same slope. And what is that slope? The slope of this line is negative 2/3. So we want to use a slope of negative 2/3. And if I sketch this correctly, my y-intercept should be less than 7. Should be down here. So might file that away. I have to erase to make room. I don't like to, but as you can see, I have a small board to work with at home. All right, so I'm going to use m equals 2/3. And so I have the start of my answer, y equals to negative 2/3 x plus b. And then to finish it, we need to use the other information, which we haven't used yet, which is what? It's the point 3 comma 4, through which the line passes. So I'll plug those numbers in, and remember, it's easy to get those backwards. 4 is the y value, 3 is the x value. So we have 4 equals negative 2/3 times 3 plus b. And here, the fraction conveniently cancels because 3 is a numerator, that 3 is a denominator. And so 4 equals to negative 2 plus b. Solve for b, we add 2 to both sides. 6 equals to b. So we predicted it would be below 7. And had I drawn the graph very accurately, we probably could have just about predicted 6 for y-intercept. All right, so let me write the answer to the problem. And by the way, when you do your work, I want to see your work, so don't erase your work. I do want to see it. Okay, so the equation is y equals to negative 2/3 x plus 6. So, and this is easy to verify. It has the same slope as the parallel line, and it's easy to verify that 3 comma 4 solved this equation correctly. All right, one other little comment. The abbreviation or the symbol for parallel in mathematics is that. And so we could say about this topic that parallel lines have equal slope. So, all right, well, you can get by with that in a math class using that symbol for parallel. That would be, I think, perfectly fine.